Hello, my name is Daniel Prangan. I'll be presenting my proposal predicting the benefits of topology optimization for thermal structural application. Outline. I'll first start with the introduction, then I'll go into the research significance and novelty, and then I'll go with the research methodology, and then I'll follow up with the work plan, and I'll end it with a conclusion. Introduction. The topology optimization method targets at finding the optimal solid void pattern of the material layout over a specific design domain within its given boundary condition and constraint, such as the mechanical load and thermal load. The topology optimization became one of the most promising techniques in the multidisciplinary design engineering field, especially the aerospace industry. At most, the topology optimization answers the question to how to place a material with a prescribed design domain to obtain the best structural performance. In terms of thermal structural application, thermoelastic topology optimization is one complicated application. This method is a design-dependent problem that takes both mechanical stress and thermal stress. This optimization optimizes the design to be stiff enough to support a mechanical load and able to release the thermal stress. For example, a topology optimization design for an effective ground heat exchanger was used, and it was concluded that the tree structure design is an effective channel to accelerate the heat releasing rate and improve the thermal performance, which provides a new way to design ground heat exchanger and other heat sinks to avoid heat buildup. In short, designing using topology optimization is a very tedious task. Computing the optimization is computationally demanding and can take several to many hours to complete a simple compliance minimization problem. On the other hand, stress minimization and the imposition of manufacturing constraint can take several days to complete. On top of that, it is very tedious to construct and create an optimized topology design into a computer-aided design-friendly and/or manufacturing-friendly product. Also, the optimization for structural and thermal analysis has some complications too, such as more design variables, confusion with the material characteristic, hard to determine thermal density conductivity reaction, as well as unrealistic parameters. Creating a metric for using topology optimization for thermal structural application will result in a better determination of whether the optimization process is worth the time, labor, and money. The objectives of this proposal is to propose a simple metric and method to determine the benefits of topology optimization for thermal structural application, to study and clarify thermoelastic topology, thermoelastic analysis, the optimization formulation, sensitivity analysis, etc. And it's also to promote topology optimization to a broader community other than engineers and scientists. Research significant and novelty. Topology optimization is a key part of the design for additive manufacturing. Unlike the other older various manufacturing process, additive manufacturing has its advantages. Additive manufacturing and topology optimization is developing and evolving in parallel with one another. As metal additive manufacturing continues to evolve, the aerospace industry is currently gearing up to reap the benefits of this technology. Topology optimization based design provides more freedom to change design than conventional design for structural products. With the evolving manufacturing method of additive manufacturing, the designer design freedom can better be realized through topology optimization that results in possibility of fabricating part at low cost and light weight. This study will tackle the effectiveness of the topology optimization by providing designer a metric. This metric can be implemented into existing computer-aided design software to determine the benefits of topology optimization for any structural application, but specifically thermal structural application. Such thermal structural application can include designing more lightweight heat shield for space vehicles to reduce payload weight and the cost of launching the space vehicle. Research methodology. For the proposed methodology for creating a metric, two methods in topology optimization will be used: SIMP and RAMP. The material microstructure, compared with the amount of material for each element, a very low stiffness will be obtained even when the element pseudo-density variable takes immediate values between 0 and 1 during the optimization. 0 means material is removed and 1 means material is required. The SIMP and RAMP equation will also be used in the sensitivity analysis interpolation of the Young modulus, thermal stress coefficient, and heat conductivity coefficient to compute the element stiffness matrix and thermal stress. In the formulation, the topology optimization problem in the thermal structural application involves thermoelastic stress load that relies on both the Young modulus and the coefficient of thermal expansion. The formulation can be expressed as a compliance minimization subject to volume constraint. For any topology optimization problem, there are two main conflicting output variables of interest: the compliance and the volume. For a thermoelastic problem, for simplicity, the input variables of interest are the Young modulus and the coefficient of thermal expansion. The initial design can be represented as a point in a volume versus compliance graph. For a problem of minimizing compliance while keeping the volume constant, there is an existing optimal solution where the possible reduction in the change of compliance are unknown. Similarly, for a problem of minimizing volume while keeping the compliance constant, there is an existing optimal solution where the possible reduction in change of volumes are unknown. The possible reduction in compliance and volume can be estimated, then normalized, that the range of both normalized values are from 0 to 1. From this, if a normalized value is close to 0, it can imply that the design is close to being optimal and therefore it's not worthy to use topology optimization. Otherwise, if a normalized value is close to 1, it can be implied that the design is far to being optimal and therefore is worthy to use topology optimization. Work plan. In order to make a topology optimization metric, first we would need to obtain an initial design and then use TO software on that initial design, obtain results, and then organize the data to create the metric. A good initial design component to analyze and obtain data is any components within the turbine engine of an aircraft. The components are great for consideration because they both endure thermal and mechanical load. Also, the weight of the components is a critical factor for the system as part of an aircraft. Partnering with or getting sponsored by top commercial aircraft engine manufacturer would be ideal to get these initial design components without executing and performing the design work. Creo Parametric, with the advanced license for Creo topology optimization, would be the software used for the experiment. For the 3D CAD modeling feature, it must have the ability to input any type of 3D CAD file format. It should be user-friendly and it should be easy to pick up. For the topology optimization feature, it must have the ability to do both static and thermal analysis, hence a thermal structural analysis. It should have the capability to use multiple objective and multiple constraints with unlimited numbers of analysis. To reduce the runtime for the topology optimization study, a supercomputer with a high level of performance as compared to a general purpose or personal computer will be used. The University of Central Florida Advanced Research Computer Center Stokes cluster has the capability to run the topology optimization solution. The specs are listed. From there, compiling and organizing the results can be used to create the metric described in the proposal methodology. Conclusion. In conclusion, topology optimization for thermostructural application is a very tedious task. By creating a metric for using topology optimization will result in a better determination of whether the optimization process is worth the time, labor, and money. From a digital transformation standpoint, this metric can be implemented into existing 3D CAD software as a system engineering tool for design engineers to make rational decisions on the optimization of the design. From there, engineers can optimize previous or new design components to make weight-critical system lighter and ease the tedious tasks. In terms of a broader impact, we hope to promote and teach topology optimization to a broader community other than engineers and scientists, such as architecture, designers, artists, and the future STEM generation.